Yeah, thank you very much to the organizers of the meeting for inviting me to give this presentation. It's a real honor, and I'm very happy to be able to share with you some of these things about the fascinating world, I think, about eigenvalues of random matrices. So when I was preparing the talk, I was sort of thinking what to talk about exactly, because it's a big field, and I realized that many of you are not experts in this field, and so I decided to make it more of an overview talk. So I will give an introduction to random matrices. We'll focus on the eigenvalues of such random matrices, and I will talk mostly about a special class of such random matrices that give rise to a very nice structure for these eigenvalues, namely they are a determinantal point process, which means that the correlations are given in terms of determinants. And then there is a connection with the orthogonal polynomials that I will talk about, and that will enable you to find limiting statements. So limits when the size of the matrices goes to infinity. That will be the main interest. What happens to the eigenvalues of large random matrices when the size goes to infinity? And there's a notion of universality that I will explain. It will come up earlier as well in the introduction. And then at the end, I will talk, depending how much time I have, about an extension of these notions, which involve so-called multiple orthogonal polynomials. And this has been the center of my own research for the last 10, 15 years or so. But I will not be able to go into any detail there, but I will just give the notions and give one example there. So I'll not be able to talk about the most recent result, but I thought it would make more sense in this audience to give a more overview talk. So what are random matrices? So, well, it's actually a broad notion, and there are many things you can do. You start with a set of matrices, and then you have a probability measure on this set of matrices. And as I said, we will be mostly interested in this eigenvalue. So the probability measure will induce a probability measure on eigenvalues as well. And so we are interested in large size limits. But what is interesting in this field is that in many situations, it's possible to find exact formulas at finite size or finite n. And these are sometimes easy formulas, but sometimes not so easy and not so. And there's also quite some luck or ingenuity required to find such formulas. And to manage them in such a way that they are tractable to what we want to do, namely to let the size go to infinity and find limiting statements. And so there are, once you have a good formula in terms of maybe an integral, then you may use classical methods from complex analysis, typically, if you have a contour integral, to find, to extract the large n behavior. But in addition to that, new methods have been developed to get these asymptotics, and most notably the so-called Riemann-Hilbert problem, which is also a problem in complex analysis. I will talk about that as well. What is interesting and also exciting to many people is that the results that come out of this for random matrices are not just restricted to random matrices. They also come up with other models, typically random models. So there are other stochastic growth models, for example, where you find the same limiting distributions as one finds for random matrices. And also the techniques sometimes are the same. But sometimes the techniques are different, and there is some mutual benefit in both directions, right? Also, some tiling problems can be used, analyzed in the same way or similar way. And also problems from representation theory. Also problems from number theory, by the way, have connections with some problems about the zeros of the Riemann zeta function, for example, on the critical line. Also have a connection with random matrices. And there are some others as well. Also applications are there. And so this is sort of part of a new area called the people who work in this area like to call integrable probability. And the applications come from physics, where most of these things originate. They originate with the work of Wigner about the energy levels of heavy nuclei, which he modeled with a random matrix. But also other physics models in quantum chaos, in quantum gravity, and many others. Also in statistics, random matrices are used and came up. In number theory, as I said, wireless communication, and many more. So it's a big field. So let me start by giving you 4 examples just to set the stage of random matrices. And the first one is a natural object. Let's think about unitary matrices of a fixed size. That's our class of matrices. And what's the probability measure? Well, unitary matrices are a group, unitary group, and a compact unitary group, and it has a natural probability measure called the Haar measure, which is invariant under multiplication on the left and on the right. And you can normalize it to make it a probability measure. So that's an example of a random matrix. Here it's indeed possible to find an explicit formula for the joint density for the eigenvalues. And it involves the product of here these distances squared. So you have the ZJs are the eigenvalues of a unitary matrix, which are necessarily on the unit circle. And there is a prefactor here, but otherwise it's a product here of these mutual distances to the power 2. And that's a common feature here in these models that I will be talking about. And you see here that they have a repulsion. So if Zj and Zk are close, then this factor in the product is small, and then it means that this is not a very likely thing to happen. 2 eigenvalues in a unitary matrix, if it's for so-called CUE, the circular unitary ensemble, 2 eigenvalues tend to repel each other. They don't like to be too close. And it means that there is a more regular spread out effect of these eigenvalues if you compare it to picking random points on just n random points on the unit circle. This is a simulation of that. And there you see much bigger gaps, and also sometimes the points that you pick maybe close to each other, closer than what you get from eigenvalues, right? And that's an important feature. Here is another example. It's called the complex Ginebra ensemble, after physicist Ginebra. And this is a complex matrix and of size n by n, and you fill the matrix with independent complex Gaussian entries. Okay, so it is a very natural thing that you may think of when building a random matrix. Again, what happens is again that you have an explicit formula for the joint density of the eigenvalues. We're dealing with complex matrices, and there's no symmetry here involved, so the eigenvalues are in the complex plane. And their joint density is again such a product of distances squared, and an extra factor here, just a 1-point factor involving only the individual eigenvalues with a Gaussian here. right? Which has to do with the Gaussian distribution that you put there. If you take, if you plot eigenvalues here from such an ensemble, and n is I don't know 1,000 or so, you find points that are in a complex plane that may look like this. And a very fascinating feature here is that they cluster in a disk. I mean, if you may want to rescale depending on n with a factor square root n, then they tend to a disk with a uniform density. So that's one limiting distribution, one limiting fact that you have here. I will not focus so much on these Genebra ensembles, but just as to set the stage for the random matrices. The third example I want to talk to you about, if you is a way to get from a Genebra matrix, you may look at G star G. So that's G star is the Hermitian conjugate, and then you get a Hermitian matrix, positive definite matrix, and this will have positive eigenvalues, or maybe 0, right? And this is called the Richard matrix, and this is a kind of matrix that appears a lot in statistics, in probability also as well, because this may come up as a correlation, as a covariance matrix, or as a model for a covariance matrix for certain data. Well, then you typically don't want complex matrices, but real. Anyway, in this setup, you can still find an explicit formula for the joint density. It has this by now common feature, right? The distances between the eigenvalues, xj, are positive and real, squared here. And again, a 1-point factor here involving just the eigenvalue xk with a e to the minus xk and xk to the power nu, and nu has to do with the difference here between the number of rows and columns in your Genebra matrix. So, and if you let n go to infinity and nu is fixed, then you find a limiting distribution here for these eigenvalues that's known as the Marchenko-Pasteur law, and it looks like this. So they go from 0 to some point. It happens to be 4. Beyond 4, you don't find any eigenvalues with probability. With very small probability, you don't find any eigenvalues. Yeah. You find a larger eigenvalue only with very small probability. And the 0 sort of, the eigenvalues cluster here around 0, and the density becomes infinite. And here is another one, maybe the most famous example, random matrix model that maybe you may have heard of, which is called the Gaussian unitary ensemble. And you may create it by adding a Genebra matrix to its complex conjugate, the Hermitian conjugate. Again, you find a Hermitian matrix with real eigenvalues, and it has the property of having independent entries, which are again Gaussian, up to their condition to be Hermitian. Right? So what's happening above the diagonal is also happening below, and you find this density, the joint density for the eigenvalues, the product of distances squared, and this product again of some Gaussian factors. And here in the large n limit, the eigenvalues cluster on some interval after suitable rescaling, which is known as a semicircle. You find it, and this is maybe a famous result from random matrices. Okay, so we focus on these eigenvalues, and the universality that was in the title of the talk refers to the local statistics of eigenvalues. So what these graphs that I showed you of these semicircle, for example, that's sort of the global distribution of the eigenvalues, where the macroscopic behavior, but the microscopic behavior has to do with the local statistics. So if you, okay, let's think about Hermitian matrices. So eigenvalues are real, and you take a large random matrix from the GUE, for example, And here is a plot of a number of them, not all of them, and then suitably rescaled so that the average distance is 1. Then you find a pattern like that. This is one sample. And here is another sample from what's called Poisson statistics. That's when you have more or less independent entries. And you see, again, this phenomenon, which we also saw in the unit circle with the unitary group, is that the eigenvalues tend to be much better spaced here from the random matrices compared to these Poisson statistics, where there's bigger gaps. And also sometimes the eigenvalues are almost the same. The repulsion here that you have between eigenvalues is happening with these random matrices and not with these Poisson statistics. And so this local behavior, turns out, is not special to these models that I talked about so far, but it holds for a large class of Hermitian matrices. And that's all. I want to say more about that in the talk. I also want to announce already at this moment that the universality, it just means that you find the same limiting behavior, right? It may fail at certain special points. So here you have the semicircle. Universality is happening here, what's called in the bulk, if there's a positive density here for your semicircle. If you are at an end point of the spectrum here, and if you focus there, then you will see different behavior of your eigenvalues. But still, it turns out that this is the same if you do it here in this situation or with a density like this. Look at this point here or that point there. This is the same endpoint behavior that's universal in many situations. So it's a universality class. There's other universality classes may happen if you, in such a situation here, if you're limiting the macroscopic density vanishes here at some interior point, then this special point, it's again different. If you would zoom in here and look at eigenvalues that you find near this point, you'll find different behavior, and there are different limiting objects appearing here. And this is sort of the theme in random matrices, and what I've been involved in as well is to identify such new behaviors, right? Find new critical phenomenon that will give rise to new universality classes. Here, if you have a higher order vanishing here compared to the usual one with a square root here, this is higher order vanishing. At this endpoint, you will find also something else. So what do you find at a typical endpoint? So if you look at the largest eigenvalue of a random matrix, and this is also one sort of universality, if you do it for the GOE, right, or some other matrix where the density vanishes like a square root, you find this universality class, and this is related to one other famous object result in random matrix theory called the Tracy-Witten distribution, and it has to do with the largest eigenvalue in a GOE matrix, but again, it is extended in many ways in many other models as well. So if you think about the largest eigenvalue of a GOE matrix of size n by n, if n grows, this largest eigenvalue will grow like the square root of 2n. If you take a difference here between this largest eigenvalue and square root 2n, and you multiply with a suitable factor, then you sort of get a fluctuation result for the way the largest eigenvalue fluctuates around its mean. This is sort of like a central limit theorem for this object. And what comes out here, this is a random variable here, which in the limit has there is a limit, but it's not the usual limit that you find in probability many times the Gaussian, which is density, but it has this Tracy-Widom distribution, which, and the graph is like here, which was first described by Craig Tracy and Harold Widom back in '93, right? So it's, what is it, 28 years ago. By the way, Harold Widom tragically passed away earlier this year. So he was a great analyst, of course, and he also did a lot of work in tuplets, determinants, and operator theory. So probably many of you will know him in one way or the other. Okay, so that's another thing you may want to know about random matrices, that there is this limiting distribution, the Tracy-Widom distribution. Okay, so what is special about all this is that there is a very nice structure. In all these models that I talked to you about, I already showed you this product of distances squared times a 1-point factor, which is common. And this is an example of what is known as a determinantal point process. So what is it? Well, so we have a so-called point process, which means that we have random points, right? These eigenvalues are random objects on the real line or in the complex plane. But let's think about the real line. And to describe the behavior of these random points, one notion that you may use are the so-called correlation functions. And they have to do in the following way. If you think about this random variable, think about the number of points in a certain set A, that's the random variable NA. Then if you choose a number of disjoint sets and take the product here, so that's like how many, the number of k points, right, you have of points 1 in A1, 1 in A2, etc. And you take this expectation value of this random variable. If you can write it as an integral with respect to just the back measure on the line, say, with a density rho k, then this density rho k is called your k-point correlation function. So let's assume that our point process has all these correlation functions for every k. Then the point process is determinantal if these correlation functions can be given as determinants. The k-point correlation function is a determinant of a k by k matrix involving a certain kernel capital K. So the capital K is a function of two variables, and you put the arguments x, you evaluate it as xi and xj, make a matrix there, and take a determinant. And if that's the correlation function, then this is, if that happens to be the case that you can do that, then you have a determinantal point process. What is special here is that the determinantal point process gives you the repulsion. Because if xi and xj would be the same, right? If two, then you have two rows that are the same and the determinant would be 0, right? So this determinantal point process has also a built-in repulsion. If you think about little k is 1, then you have the kernel on the diagonal, and that would be the 1-point correlation function. That's just the density of the eigenvalues or the points. So that gives you like the semicircle law in some sense. Okay, so all these examples that I showed you are indeed determinantal. Though I should maybe emphasize that this is one point of random matrix theory where you deal with these determinantal processes. People also look at other models, but I will stick to those. And what does it look like, this kernel, in this case of a GOE? This is the density of eigenvalues. Well, it involves the orthogonal polynomials with respect to the weight function here, which is the Gaussian weight. And these orthogonal polynomials are known as Hermite polynomials. And so you take a suitable scaled version of them so that they are orthonormal with respect to this e to the minus 1/2 x squared weight function on the real line. And then you make this sum here of n terms involving these polynomials at x and at y, and a prefactor, which happens to be the square root of the weight function in x times the square root of the weight function in y. This is also a reproducing kernel, right? For those of you that are interested in reproducing kernels, this is also a reproducing kernel for weighted polynomials on the real line. Okay, and so there are other expressions for this correlation kernel in this specific example. There is a so-called Christoffel-Darboux formula that allows you to rewrite this sum with n terms as in this way. And using special properties of Hermite polynomials, you can also rewrite this as a double contour integral. And this last formulation is very useful for asymptotic analysis. Once you have a double integral, n is a large parameter, then you may use techniques from asymptotic analysis, the saddle point methods, to extract the large n behavior of this object here. And such analysis was done already many years ago by Rodin and Mehta and Dyson. They were able to obtain such a limit. Take this correlation kernel for the GUE, take these rescaled variables that you concentrate your attention on at 0. You're looking at close to 0 when n gets large. This is the proper scaling that you want to do. And then this limit tends to an object which is called the sine kernel, involving the sine function. And yeah, that's what you get out of their analysis. And it means that if you think back to these k-point correlation functions and you do a rescaling of your points, right? So you have your eigenvalues, you rescale them in this way, multiply them with a suitable square root n, basically times a suitable number, some constant. That these rescaled points, they have rescaled correlation functions like this, that these have a limit. Namely, they are given by a determinant of involving the sine kernel, right? That's what it means. And this expresses the fact the sine kernel generates another determinantal point process with an infinite number of points, and they are sort of a model for what you see, right, for large n. And this is the universality result that happens in the bulk. At the edge, if you focus on the edge is like 2 times square root n. You center and scale around there with a suitable exponent here, the 1/6 exponent. Then you get another limit, which involves the so-called Airy kernel. It involves the Airy function, which is a special function that can be expressed as a Bessel function as well, but it's a solution of this simple second-order differential equation that decays at infinity, right? At plus infinity, and it oscillates on the negative half-line. So the graph here is in red. The blue one is the derivative of the Airy function. The Airy function models the behavior at the end point. And the Airy function also features prominently in one description of the Tracy-Willem distribution that I mentioned before. Okay, now as I said, these limits, they are not special to this GOE or the CUE or something like that. They happen more broadly. And so they're really fundamental phenomenon, and it has been proven in great generality. In many ways, these things have come up, and within random matrices, you have two broad classes of ensembles. The ones that are called invariant ensembles, also called unitary ensembles in this setup, in this setting, that are invariant under unitary transformations, conjugation here. And they take the a form like this. dm is a Lebesgue measure on n by n Hermitian matrices. V is some potential function. For the GOE, it would be V of m is m squared. And you take a trace, right? And there's a scaling little n here that you do. And then this is in an exponential. And the V of m should be such that V goes to infinity if you go to infinity in one way, so that this density decays indeed at infinity. For example, V of m is m squared, but you may have another polynomial, higher ordered polynomial of even degree, or something more general. So these are called invariant ensembles, and for these models, the universality was proved in the 90s by Pasteur, Sharbina, Plecher, Itz, and Dived, Krecher-Bauer, McLaughlin, Vindakidis, and so, with the methods I will talk about later on as well. There's another class of random matrices called Wigner ensembles, after the physicist Eugene Wigner, which are characterized by having independent entries. Apart from a symmetry condition, right, that you want Hermitian or symmetric matrices. But otherwise, the entries of your matrix are independent. And the GOE is in both classes, invariant and also independent entries, but this is the only one actually. So this is otherwise a disjoint class from these ones. And here the bulk universality, right, to find the sign kernel was done more recently, like around 2008, by two groups of people, Erdős, Péchet, Ramirez, Schlein, and Yao, and other works by some subset of these authors, and also works of Tao and Wu around the same time. They use different techniques. Right? So I will focus on these invariant ensembles. As I said, this is the typical form. The Zn, by the way, is just a normalization constant to make it a probability measure. And this is, so if you change your matrix to U times M times U inverse with unitary matrix U, then this becomes invariant under such a transformation. So this is important from physical applications, that your model is independent of, or does not depend on a change of basis. Right? What is special here is that you find an explicit joint density of eigenvalues, right? Which is of the form that we already saw a number of times, this product of distances squared times this product of one-point functions, this e to the minus n v, which now involves this v, right? The v here is a function, say a polynomial. In the GOE case, is like x squared. But in general, the v comes in here. And because of this special form, it is determinantal. The product of distances squared forces it to be determinantal. What you have here is that if you think about large n behavior, then you may think about it this way, that you want some collection of some distribution of points that sort of maximizes this joint density, right? That's a likely configuration of eigenvalues. If this is small, of course, then it's not so likely. So you can think about to maximize this expression here. And if you take a logarithm and take a minus sign, divide by n squared, then in some continuum limit, you find this problem, that the limiting eigenvalue, the limiting density of eigenvalues, the macroscopic behavior of the eigenvalues is characterized by this problem to minimize this, what's called energy function. So you have a double integral here of this logarithmic kernel times psi of x times psi y. That psi would be your density of your the limiting density of your eigenvalues. That comes from the van der Monde factor here, the product of distances squared. And this term with a v comes in integral of v times psi x dx. That this comes in because of the v, which is in this setting is sometimes called an external field. And in this setting, you have a balance between the repulsion that you get from this product of distances squared and the external field, which acts also as like a confining potential. And that's why this parameter n here is important. If you don't have this n here, then the confining potential is not strong enough and your eigenvalues would move to infinity. They don't do that in this setup, provided v has a sufficiently large increase at infinity. And you may find these limiting densities like this. It depends on v. This correlation kernel that comes with this in this model is of a similar feature as what one has with the GOE. For the GOE, there was such a formula involving the Hermite polynomials. Here, it depends on v. And you need the orthogonal polynomials here that are orthogonal with respect to this weight function e to the negative nv. Okay, so there, again, the v decays, v increases at infinity and minus infinity, so the weight decreases there. There will be this set of orthogonal polynomials, and they play a role here in a similar way as the Hermite polynomials do that for the GOE. And so actually the asymptotics of the orthogonal polynomials here in this setting is closely related now to these questions about universality, about the limits of this correlation kernel in the large n limit. And so, and you may also think about that, think about it this way, that if you think about the nth degree orthogonal polynomial here with respect to this weight, that's a deterministic object. It has real zeros, and these zeros are sort of, you can think of them as being a model for the random eigenvalues of the random matrix. Right? They behave in the same way when n goes to infinity. That's what happens here. And a major tool that can be used to analyze this is this steepest descent is the Riemann-Hilbert problem that I'll talk about next. And that you may think of as being a substitute for the analysis of integrals that you have for example, for Hermite polynomials. You have contour integral representations. For these general orthogonal polynomials, there's no such thing. There's no general useful integral representation for these, but there is this Riemann-Hilbert problem. That's due to Dijf-Zhao. In general, I mean, the steepest descent analysis that this is useful for asymptotic analysis has been worked out by Dijf-Zhao, and for this particular case, the Riemann-Hilbert problem for orthogonal polynomials was first formulated by Fokas-Itzkitayev, so early 90s, and it takes this form. So now we go to the complex plane, and we get a problem in complex analysis, if you wish. You look for a matrix-valued analytic function, which is made analytic in the upper half plane and in the lower half plane. And on the real line, you specify that there is a certain discontinuity. So the plus and minus boundary values on the real line. So the plus boundary value is the limiting value from the upper half plane. The y minus is the limiting value from the lower half plane. They're not the same, but they're connected with this jump matrix, which involves the orthogonality weight. And you also have a certain behavior at infinity. if z goes to infinity in a complex plane, your y here behaves like the identity matrix plus smaller terms times this diagonal matrix, z to the n, z to the negative n. Okay, so this was formulated by Fokas-Itskitayev. In this, there is a unique solution. You can write down the solution. I didn't do it, but it's not, once you know that there is a connection with orthogonal polynomials, you can do it. The 1-1 entry of the solution is actually the orthogonal polynomial, but not the orthonormal one, but the one that's monic. So the leading coefficient is 1. Gamma n is the leading coefficient. So you divide by the leading coefficient and you get a monic polynomial. That's the 1-1 entry. And the 2-1 entry is the monic polynomial, well, not the monic, but orthogonal polynomial of degree n-1. And actually the other entries in the solution here, the second column, are Cauchy transforms. You can also write down the correlation kernel explicitly in terms of this of the solution of the Riemann-Hilbert problem here. So it involves the solution here at the point x. So you take the plus boundary value for x on the real line, and also for its inverse. This should be a plus as well. Actually, it doesn't really matter. At the point y, you take these row and column vectors, and there's some scalar prefactor here. And it turns out to be the correlation kernel. And you should think about this as sort of a substitute for a contour integral formula. Right? So you have the Riemann-Hilbert problem depends on the parameter n. There's also a parameter n here, okay, but in here as well, there's n here and here. And you want to extract information about the solution of this Riemann-Hilbert problem as n gets large, and then use it to get limiting behavior for this correlation kernel or scaled versions of it. So that's what this Daift-Zhao method does. So I don't have time to go into any detail there, but that was done by Daift and his group of people in the late 90s. They indeed proved that there is a sign kernel limit if you are focusing on a point in the bulk. So if you have a point x0 where your density is strictly positive, and you make this rescaling, then this Kn, this correlation kernel, has a limit, which is this same sign kernel. And also you find the airy kernel at the edge. There's new things happening, as I already indicated, if you have critical cases. For example, if your density here vanishes in an interior point, or if it vanishes to higher order at some edge point, then you don't find the airy kernel. The simplest case for which this happens is a quadratic potential here, double well potential, where you may find this situation here. And there's also, yeah. Now, if you then focus around 0 here, you find new limiting kernels, different ones, that are much more complicated to formulate than the sign kernel or the airy kernel. They involve special functions also, but there are special functions associated with so-called Pain-Levé transcendence, Pain-Levé functions that satisfy nonlinear differential equations. Right, so this is also very much a theme. These Pain-Levé functions also appear, by the way, in the Tracy-Willem distribution. So there's a coincidence here that the same functions actually appear in the Tracy-Willem distribution and also in the description here. And this was worked out by Blecher and Itz with my student Tom Kleijs at the time, and another paper with Kleijs and Van Lessen, where they talked about treated the endpoint here. So, but I will not talk more about that. So in the remaining, 10 minutes, I want to briefly indicate some extensions that I'm involved in for other models, where we want to do similar things, but yeah, but some more complicated models, and also some new critical phenomenon can happen. And the analysis is done by means of multiple orthogonal polynomials. So that's an extension of orthogonal polynomials. So this is sort of part of a long-term project that I have since for about 15 years now. There are other models, matrix ensembles, but also maybe more generally, that lead to determinantal structure. Not more complicated than the ones that I showed you so far. And this was actually the first model that I worked on in this direction. It's called the random matrix model with external source. So you see the same feature here with the V of M, but there's also the deterministic matrix A here times M. That is known as the external source. But there are other matrix models that also are interesting and have different features and can also be analyzed. The so-called two-matrix model, where you have two coupled random matrices. The normal matrix model, there's also was successful also with products of random matrices and so-called mutually bordering ensembles, and most recently also to non-random matrix, but still related random tiling models. And so we want to analyze these models with extensions or analogs of the notions that I talked about, namely the orthogonal polynomials, an extension of a Riemann-Hilbert problem, if possible, and also this equilibrium problem, which gives you the microscopic density that you may also have to generalize, which is known as an equilibrium measure. I want to talk about that. So I'll talk about these multiple orthogonal polynomials. What are they? So they are an extension or generalization of orthogonal polynomials, where you have not one weight function, W, but a number of them, say R, at least two. And you have also some multi-index, some N1 up to NR, some natural numbers. And then you look for a polynomial of a certain degree, which is the sum of all these indices, satisfying certain orthogonality. So what is this? You have this polynomial, you multiply it with one of these weight functions, and then polynomials x to the k, where k goes from 0 up to this multi-index nj minus 1, the jth component of the multi-index minus 1. It means that you have nj orthogonality conditions with respect to the jth weight function. And you do that for every j from 1 to r. So in total, you have this number of conditions, little n, number of conditions on a polynomial of degree n, which has n plus 1 coefficient, and you want it to be monic, so you specify the leading coefficient. And so there may be a unique solution, or maybe not. It depends. There's a nice survey about this multiple orthogonal polynomials, by the way, in the notices of the AMS some years ago by Martinez Finkelstein and Van Assen, if you want to read more about that. So what is nice is that these multiple orthogonal polynomials indeed are related to random matrices for some cases. I'll show one of them the next slide. And what's also nice is that they satisfy that they can be characterized by a Riemann-Hilbert problem. So that's one of the main tools for asymptotic analysis. But the feature is that the size of these of the matrices is not 2 by 2, but it depends on R. So it's R plus 1 times R plus 1 size matrices. So, and again, you have a jump on the real line, which involves this jump matrix, which has these weights here on the first row in your jump matrix. That's the behavior at infinity that you also need to specify, and that's where the elements, the entries of your multi-index appear, N1 here and NR there. So if your multiple orthogonal polynomial exists, then there's also a unique solution of your Riemann-Hilbert problem here. And the one entry is indeed this monic multiple orthogonal polynomial. And yeah. And so this is then very useful for asymptotic analysis. So let me then go briefly through this case where you have this external source model. This A is some fixed matrix, and the model depends only on the eigenvalues that you have of your external source. Let's call it A1 to AN. And there's an explicit formula for the joint density. This was derived by Kami and Saint-Justin in the early 2000s. It has this product of distances, but not with a square, but instead there is a determinant. And this is also a determinant in a way. This is a van der Monde determinant and another determinant. So we have a product of two determinants still. The way to get rid of the eigenvectors here is by means of a formula called Harish-Chandra-Itzukson-Zubair formula that I will not talk about. But what happens is that if you think about this polynomial, you have your random matrix, you take its characteristic polynomial and you average over the random matrix ensemble, you get a polynomial of degree n, which is deterministic, and it happens to be a multiple orthogonal polynomial. What are the weights? The weights are these e to the minus nv with a linear shift here depending on the eigenvalue of capital A. And the multi-indices are the multiplicities of these eigenvalues. So if of these, say you have R distinct eigenvalues, then they come with multiplicities. That's the multi-index. And you have another formula for the correlation kernel. More complicated, but it has a similar feature as what we saw before. And then one thing that you can do is to analyze this model, for example, with the case where this A has only two distinct eigenvalues, say plus and minus little a, say with equal multiplicity. I take a Gaussian V, and you have a new critical phenomenon depending on this parameter little a. Eigenvalues may be on one interval or on two intervals, and they also, for a critical A is 1, be on two touching intervals. But it's different. It has an exponent here 1 over 3. And it gives rise to new special functions that you need called Pearcey functions, Pearcey integrals. And this can be analyzed in detail. And I did it with Pavel Blecher some years ago, actually. And we proved this limiting behavior. Okay, my time's up. So thank you for your attention. And so maybe there are questions. Thank you.